Okay, thank you. Welcome to this second talk of this afternoon. We have now Elke Messner from Hofer Institute of Integrated System and Device Technology, Erlangen, Germany. Elke will speak about defect in nitride semiconductor materials and their relevance on the electrical devices. Elke, the podium is yours.
Thank you. So this afternoon we will have another lecture. We heard this introduction of Geoff Delin. He was talking about materials in terms of hetero-epitaxy, and I now will give you a brief introduction about what semiconductor crystal really means as a whole crystal. So I will be shortly talking about technology of nitride crystal growth, and then I will show you what is really distinguishing an ideal crystal from a real crystal. This is what we are talking about if we have made a crystal ourselves. So normally we are dealing with real structures. So the real structures have some disadvantages compared to the theoretical form of a crystal. So we're talking about defects in a semiconductor and the type of the defects that are there, how we can visualize them, where the dislocations or defects may come from, and actually what they are doing, what nature do they have themselves, and what they are doing to an electronic device. So why don't we want to have dislocations at all? You heard a talk from Geoff about the problems associated to hetero-epitaxy. I will pick that up only shortly, not in order to generate too much redundancies in both of the lectures. And from that it comes up that we have some certain need for native substrates, of course, if we want to avoid all these defect kind of stuff. So what you will hear is something from crystal growth over defect structure of semiconductors, electric properties, what they are doing to electronic devices, and so on. This is like rushing over the planet in 1 month. So it's very brief, and you may see that the one or the other things are only briefly covered. So what can we say about crystal growth? This is maybe not familiar to all of you. So I'm a crystal grower. So what I always did is I cared about physical properties of crystalline matter. And the best of all for us, crystalline matter is a big crystal. And a big crystal we want because the crystal material, so a pure solid material, which is a crystal, normally has extraordinary properties which you cannot have from other type of material. So you can have other solid matter, which can be ordered or disordered. You can have a ceramic, you can have a metal, you can have polycrystalline material, and so on. You can have glasses. But they all do not have the same outstanding properties like a pure crystal has. And here you can see all these man-made crystals. So it's all artificial crystals. It's not what you can find in nature. But you see that they can have different sizes. They can have a very large size, like the silicon crystal. They can have facets. They can have no facets. But the idea of growing a crystal is to give them not a natural shape, but to give it a, let's say, a round shape or some shape that helps us to slice all the crystal in that usable shape that we want, which is, for the electronic cases, a wafer, which is a round sheet. So what does the crystal really mean? What does crystal mean? Crystal has several aspects. So if we talk about the ideal crystal, which is the theoretical thought about what a crystal is, it's meant that it's a strict geometric arrangement of atoms in form of a lattice, which is 3D and infinite and perfect. So just by definition, an ideal crystal does not have any defect. So we call that structural arrangement of atoms, we call the crystal lattice. And of course, you may have all attended crystallography. This is what was my favorite. And the crystallography also tells you what crystal lattice you're dealing with. It has point groups, symmetries, symmetry actions, permutations, all these kind of things. And if you have one individuum, it means that you have one single crystal, we call it, or volume crystal, or a bulk crystal. You may have heard all these words. And it means that you have one individuum which has, from the bottom to the top, only one perfect arrangement of atoms in a crystal lattice. So if you have a single crystal with defects, or you have a twin, or you have polycrystals, this is not what we call an ideal crystal anymore. This is what we call a real crystal, and this is what I will come back later on. So if we think about crystal growth and the type of crystals that we would need for an application, like for an electronic material, there are various choices. So I told you about the single crystal, the volume crystal, which is a big body of a crystal ordered in atoms from the bottom to the top. This is what you see here. So it's one large individuum. And beside that, you can have crystalline layers or epitaxial layers, and you heard this from Geoff before. This epitaxy is a special kind of a layer, which means that you have a strong orientation relation between a substrate that you put and the crystalline layer that you are growing. Of course, crystalline layers can appear in a different form, so you can have polycrystalline layers or nearly single crystalline layers, which eventually have a strong preferential orientation. And here you see an example. You see that there is polycrystals, small crystals, but they do have an orientation relation to the substrate, and they do have an orientation relation amongst each other. Now it depends on the twists and tilts between those crystals, whether they are rotated to each other or not, how good those grain boundaries may vanish. And you may have something which is kind of a large individuum in form of a crystal layer on some substrate. And if that has also a strong geometrical relation to the substrate, you call it an epitaxial layer. And the epitaxial layer is that what is important for building up an electronic device. So an electronic device is just a set of many epitaxial layers. So how do we do crystal growth? You heard how one can do epitaxy, but actually it's the same in growing a volume crystal. So first of all, you have to find the right crystal growth technique, which is not easy itself. So you can, in principle, divide it in 3 cases. So you always have a raw material, you always have to mobilize some building blocks, and you have to order the crystal with a perfect lattice. So those are the 3 steps that you have to do. So you have some raw material that can be a powder, for example, and you have the mobilized building blocks, which can have a different form. And then the ordering of the crystal happens by a process which can be condensation, which can be freezing, or just a deposition from outer gas phase. So in fact, you have 3 steps to do to order a crystal, and you have 3 choices. So either you can evaporate your raw material, or you can melt your raw material, or you can solve it in some solid. And then from out a gas, from out a melt or a solution, you generate the ordered crystal by a thermodynamic process, more or less. On the other hand, crystal growth is always a combination of thermodynamic and kinetic actions, because you're dealing with a real system, not with an ideal system. So how to find the right process for a crystal growth? So how can we grow a gallium nitride or aluminum nitride crystal? This is a process that does not exist so far, or it exists in some processes, but it's not completely solved. And some years ago, or so many years ago, it doesn't even exist what would be the right choice for a process for growing the nitride crystals. So as I said, you have 3 choices. You can either melt your material, you can evaporate it, or you can solve your material in something. If you want to melt it, it's essential that you have a meltable material. And this is the case, for example, for the well-known silicon, for the gallium arsenide, for the sapphire. And you have different growth techniques, like the Tucholsky growth technique. You have the VGF, it's called vertical gradient freeze technique. It means that you're moving an isotherm to your melt in order to solidify your crystal. You have the Chiropoulos growth. Chiropoulos, this is, for example, the technique where the sapphire is grown with. And if you have a gas phase growth, it means that you cannot melt your material, but you can evaporate it. But evaporation can happen differently. So you can evaporate a melt or a material congruently or incongruently. If it dissociates early, then you have a problem with evaporation, which is the case with the gallium nitride, actually. If you just would put temperature on this, it just would dissociate. But anyway, the gas phase processes, like the MOCVD process that you heard from Jav, is a choice for growing gallium nitride and aluminum nitride, and also for the silicon carbide. The PVT growth, physical vapor transport growth, was established for silicon nitride, for silicon carbide first. And then it was adapted to aluminum nitride, and gallium nitride doesn't work so neatly with that, so we need some chemical-assisted process, which I show later. So if you have non-meltable, non-evaporatable, this is really the worst corner of the cube. So this is the worst choice. And the gallium nitride you see still here. So the gallium nitride for the crystal growers really is the most difficult material we ever had amongst all the materials that we want to grow crystals out of in the last tens of years. So the choice is also the flux growth. You can do a high pressure growth, and the monothermal growth, and both of those, the HVPE growth and the monothermal growth of gallium nitride, is nowadays the most promising both technologies that the crystal growers try for growing a gallium nitride massive crystal. So what is the problem really? As I said, the problem is the thermodynamic in that case. So actually physics and chemistry is against the crystal growers in that case. And you see the temperature pressure diagram, which is the phase diagram, of course, or one of the phase diagrams you can take, and you see that the gallium nitride is decomposing. So you have the nitrogen as a component, and of course, if you dissociate the material, it means that the gaseous component will just disappear from the component, and you will form some whatever nitrogen molecules, and they just go away and they leave about the gallium as a pure metal. And this is what you don't want. And this is also causing problems for the pure PVT growth. So if you just evaporated the component, then you have the pure gallium and the nitrogen, and the gallium coexisting phase is a liquid phase. So you may know that the gallium is one of the rare materials that exist in a liquid phase. And the gas pressure is not so nice, so it's like low and not what we want to have. The nitrogen is a slowly or hard reacting component, so we have a problem to grow it from the gas phase. So you can melt it. You can melt it at those conditions, which are not nice conditions for a technical application. So you have something like 60 kilobar as an equilibrium partial pressure at very high temperatures. So you have something above 2000, which is something one could attain, but attain a temperature above 2000 at 60 kilobar is something that is technically not very nice. So this would be the technique of melt growth, which is not the way to go, because you will never manage to grow larger crystals under such harsh or such technical difficult conditions. So for the gallium nitride, except at very high pressures, the classical melt growth is not possible, nor is the PVT growth favorable, because you have this dissociation problem and the problem with the not reacting nitrogen. So the trick that we are doing is, we're doing a gas phase process like the PVT process, but I would say it's a chemical assisted or chemical mediated gas phase growth. So we add a chemical compound and we form a reaction which helps to transport the gallium nitride in an easier way, and we, instead of the nitrogen, we add an ammonia, which is a more reactive component. So what you have is you have some source, which is a gallium source here. It's a pure gallium under a certain temperature, and you flow some hydrogen chloride on top of over this gallium source. You form the gallium chloride, and on the other side, you add the ammonia flowing over that, and both of those components come together close to the substrate. And in a reaction, gallium chloride plus ammonia, you form finally, over this intermediate reaction, you form then the gallium nitride plus an HCl, and you have the gallium nitride as a crystal here. So this is what we do. It's not that easy. It's such that we can grow crystal bodies on the order of like 5 to 10 millimeters in length, which is for a full crystal body, as you saw before, which is very short. So it's only a small length that we can grow with a growth rate of, let's say, 100 micrometer per hour. And it's still difficult to stabilize the processes for a long time because you have these reactions, you can have parasitic reactions, you can have depositions all over the reactor, and this is all causing problems to the crystal growth process. So you see this on the crystals, of course. So as soon as a crystal growth process is not perfectly stable, also in terms of its thermodynamic and kinetic, you will see it from the properties of the crystals. And here are some examples. This is how a crystal can look like from a HVPE process. You see that the diameters are small. It's like 2-inch diameters, but we're working on the 3-inch diameters and up to 100 millimeters. So we have visible attempts also. We have own crystals that are 3-inch in size. You see that the thickness is small, and you see that there are a lot of growth defects like surface defects, surface pits, and so on. And of course, they have to go away because otherwise the crystals won't be usable for slicing a wafer for electronic purposes from that. And you see that the crystals can crack, and all these kind of things is that we don't want. You see that the crystal is colored, even though if you slice a wafer from it, and coloring, of course, means that there are impurities, because you're talking about gallium nitride, which has a band gap above 3, so the material should be transparent for visible light. And it's not, so it means that there is some junk hanging in the band gap. So this is what we see. But there are native seeds available. There are no native seeds available for the crystal growth, but there are some wafers, some numbers, small numbers of available for other things that can be tried, but the costs are quite high, like the $2,000 per 2-inch substrates. The dislocation density, however, is like 10 to the 6. It's much smaller than what you can attain in an epitaxial layer. So if you have an epitaxial layer in hetero-epitaxy systems, you talk about dislocation density like 10 to the 8 or 10 to the 9. So you have 2 or 3 orders of magnitude lower, and this is actually what it's good for, and this is what we should do and aim for. So the alternative, as I said, is the monothermal growth method for gallium nitride, and a monothermal is something that is comparable to a hydrothermal growth process. Hydrothermal means that you work under supercritical water conditions, under higher pressure and temperature, and this is actually a production method that is used for producing many tons of quartz crystals every year. So hundreds of tons of quartz is produced by the hydrothermal method. Now you go to supercritical ammonia, and you have a process which is kind of comparable, and this is the idea what the crystal growers want to try also. Of course, the temperatures are kind of moderate, it's okay, but you have to face these higher pressures on the order of 3,000 to 6,000 bar, which is not too high, but it is still a challenge with the supercritical ammonia because it's much more corrosive than any water under these conditions can be. So it's still a difficult technique, and it's still under development, but the crystals are pretty precious. So you see that also the variety is, of course, there, and this is what was already brought up by Peter Moon so far. So if you take a native substrate, any of the native substrates is different than another. And you can see this from the row of crystals, for example, here. They have different diameters, they have different impurity contents, and so on. So it means they have slightly different lattices. And they, of course, have a very low, so the lowest we know now, dislocation density comes from a monothermal gallium nitride crystal. It's like 10 to the 4. So it's 4 or 5 orders of magnitude lower than the dislocation density in an epitaxial layer. And this is what is the competitor. Silicon crystals, which are grown after the Tucholsky process. So the Tucholsky process is a process where you melt the gallium, where you melt the silicon. You have a silicon melt which is dipped with a seed, so a very thin seed, and it's dipped, and you widen the diameter, and you pull out the crystal to the top of the machine, like you can see here. So this is the crucible with the melt. You dip the crystal somewhere and seed it, and then you pull it out to the top of the crystal growth machine. And what comes up is some meter-high crystal, and this is a technique which produces the wafers for the gallium nitride on silicon hetero-epitaxy. So this is our competitor for the crystal growers. And this is a really harsh competitor. because you have the crystal, you can do the crystal growth, you can do the crystal growth cheap, it's very mature. You slice the crystal in a wafering process, you polish it, and you have many of those silicon wafers with different diameter, and it's very, very established technique and very, very cost effective. So on the other hand, we're dealing with real crystals, and an epitaxial layer is a more than ever real crystal because you have a lot of defects there. So a real crystal means any deviation from the perfect lattice, the perfect periodic arrangement in a crystal with imperfection. This means that we have a real crystal, not an ideal crystal. And a real crystal, by definition, has defects. The defects you can divide by their dimension. This is what we do. So we have point defects, we have line defects, planar defects, and volume defects. So point defects is something that we always have to do in semiconductors with. So it's vacancies, interstitials, can be impurity atoms, and all those is what we maybe don't want. But what we want is doping atoms. And doping atoms is nothing else than a point defect. So we have line defects like dislocations. We have planar defects, which could be extra surfaces. It could be stacking faults. It could be grain boundaries, which form twins, and so on. And we have volume defects, which may be some precipitates, or in the case of silicon carbide, it's like poly inclusions with a different polytype and so on. Anything that is non-uniform and which expands in all dimensions. So what can you have such a vision or imagination about what defects in a semiconductor crystal are? So we have the atomic arrangement. We can have extra atoms, so it's interstitial atoms. It can be an impurity or dopant atom. It just sits somewhere because it has to take some space. And you can have self-interstitials. You can have missing atoms. And what you also immediately imagine is that you can have that all those defects, they are causing strain to the surrounding. So they are doing something to the surrounding. If there is an atom missing, of course, the surrounding is differently happy. It's not so happy as before. So you cause some strain, and the lattice maybe has to expand. So if you introduce an extra layer, which is, for example, an edge dislocation, then also the surrounding has to adapt to that place in some way. So you have plastic deformation, whereas the dislocation represents elastic deformation, whereas the dislocation represents a plastic deformation place. And so you have all these type of defects that we have to deal with. So what causes a dislocation or a defect in a crystal? And now we come back to the Gibbs free energy, which is maybe one of the most fundamental properties in a crystalline matter or even in a solid matter, which can be expressed as G or delta G. So you can observe deviations or you can observe an absolute value. And so this defines kind of a potential state for a crystal if we consider thermodynamic units like the entropy and the total energy of the system. And we have the minimization criterion, which you already heard from Jav. So it means that any matter tends to minimize its free energy. And this is what a crystal does with using a dislocation. So it's nothing else that a crystal do. So the Gibbs free energy of a crystal depends on its defect content. And you see that if you put these on a row with increasing Gibbs free energy, the point defects also lay on the very left side. They lay left side from the ideal crystal. So it means that some concentration of point defects mediate the Gibbs free energy in such a way that the crystal feels happy. So it means it causes a higher entropy, and in turn it has a lower Gibbs free energy. So no crystal can be grown without point defects. This is a real crystal. Then you have the ideal lattice, and then, of course, the dislocations, grain boundaries, precipitates. They all help to increase Gibbs free energy, so the extended defects can be avoided in principle, but we have to do some thermodynamic action in order to lower the Gibbs free energy and make the crystal happy. So what does the defects do now for a current flow? So why do we consider defects at all? So we have a precious lattice, and And maybe you can envision an easy experiment. Imagine if you take all the men and you arrange them in a regular lattice, all the male ones amongst you. And then you form all these lattice places in a perfect arrangement. And then we take the ladies as the carriers, as the charge carriers, and we send them through the row of the male crystal. So they can move easily, if it's a perfect crystal, through the rows of the men. But now if you displace yourself, and we still send the ladies, of course, as charge carriers, because they're more attractive. So you send them through the row of the men, and then eventually they bump into someone. And they have to get around them. This is, you scatter the carriers. So you just have to get around these disturbances. And in places where you have an attraction among individuals or places to the ladies' carriers, they may be trapped. So they may be caught away. So you flow a current through the crystal, and at the end, you observe this current anymore because all your charge carriers are going away. They're being trapped or caught or scattered. So finally, a semiconductor crystal must be as perfect and as clean as possible to avoid such effects. And the defects are always unwanted and deteriorate the physical properties of the crystal and the performance of the semiconductor. Only some defects, like the doping atoms, are really useful. They are, in fact, impurities, but in a controlled meaning. So let's consider some two types of dislocations, which is a screw dislocation and an edge-type dislocation. And we express the nature of a dislocation in terms of a dislocation line and its direction, and in terms of a Burgers vector and its direction. And this is where we can distinguish dislocations and what they do. And we can describe reactions, so it's a very useful to things that we're dealing with. And we can also define what dislocations can do and where they can move along. So for the screw dislocation, it is said that the Burgers vector is parallel to the dislocation line. So you see a core of dislocation here. The Burgers vector is the green one, and the dislocation line is along that. So as long as it's parallel, you talk about a screw dislocation. And if the Burgers vector is perpendicular to the dislocation line in a lattice, you talk about an edge-type dislocation. So a screw dislocation can move out of the plane, as you can see here. It can have a surface component on the planes. And moving a screw dislocation always means that you need an action of climb, or glide effort, which is larger than the effort if you move a dislocation along a singular plane, which you can do with an edge dislocation. So if an edge dislocation moves, you can move it in a set of glide planes or equivalents, symmetric equivalents of glide planes, and it does not need to move out of the plane. So you see that there is a different action that you have to do, for example, to a dislocation to move it. This is just to show you what we have present in gallium nitride to the majority. There are others as well. I will leave out the stacking faults and all these kind of things. But basically, we have three very typical arrangements. And in a gallium nitride, you have the hexagonal basis plane. You have the prism plane, which is the hexagonal prism sitting on top of this. And you have some pyramidal planes which can go through this unit cell in an inclination. So typically, we find dislocations that have their dislocation lines along the growth direction of the crystal, which is the C direction. So this is perpendicular to the basal plane. And you see that we have a threading edge dislocation, a basal plane dislocation, it's laying in the basal plane, and a threading screw dislocation. And there are, of course, these abbreviations for that. And I show you how they look like, because I will show you in a short excursion how we can visualize the defects. And all defects normally means that your lattice is distorted. And as soon as a lattice is distorted, you can use the Bragg's condition, so the Bragg's diffraction condition, for visualizing. So as soon as you have a distorted lattice, the Bragg condition will not be true for this place where you eliminate or where you bring your crystal to a diffraction, and it means that it creates a contrast which you can make visible. And this you can do by different X-ray or electron diffraction techniques in a microscope or diffraction equipment. And you can see here that you can also identify by defect selective etching. And then in a TEM image, you see from the top what is the strain field around the dislocation, and you can visualize where the dislocations are, and you can also identify them by their Burgers vector and by their line vectors. And you can see here in a cross-section, this is a gallium nitride layer on a substrate. In a cross-section, you see all these dark lines, and all these dark lines is the visualization of the strain field of a dislocation. So you don't see the dislocation itself. You see the strain field around the dislocation line. This is what you see with diffraction. So here you can see it a little larger, and what you can also see here, and what is important, you see all these lines, but you see that they are straight lines, but they can be different. They can make loops, and they can react with each other. You see here a bundle of dislocations, and they can combine together, and on top of this, there is only one single dislocation line or a different number of dislocations lines, or they can change nature. And this is something very important. So dislocations can never just stop or disappear in a crystal for energetic reasons. So they have to do something. They have to grow out to a surface to annihilate. They have to react with another dislocation. They have to move and let's say, annihilate with a dislocation of a different type, and so on. So getting rid of a dislocation requires some action, which takes into account the thermodynamic, so the energy of the system, driving forces, and of course the structure and direction, so the crystallography of the system. So what is typical for a dislocation? So there are some typical rules that the dislocation normally tend to follow. All the dislocations, as I said, have a strain field around them. Now the changes that you do to that strain field are always energetic actions. So the total energy of a dislocation, you can see here, it's a sum of the elastic energy that you have in the strain field and the energy that is stored in the core. So the total energy of a dislocation is also proportional to the length of the dislocation line. So in order to follow the minimization principle, a dislocation always tends to be as straight as possible. Because if it makes detours, it means that the dislocation line becomes longer, and this is what, for energetical reasons, is not favorable. The dislocations always want to have a shortest possible dislocation line and the smallest possible Burgers vector. So if you have a long Burgers vector, it means that each dislocation spans over many lattice planes. This is not fortunate because the energy effort would be too large. And for the minimization principle, then the system tends to break this dislocation, to dissociate it in a dislocation with smaller Burgers vectors. And the edge dislocations always have a larger line energy than a screw dislocation. And this also tells us something, because screw dislocations are energetically very happy. And they don't want to do anything. They don't want to move because energetic action is too large. They are happy in their configuration. And in the gallium nitride, we have a lot of screw dislocations present. And it's really hard to get rid of those because they feel so happy. Now, what can we do for moving a dislocation, or what will happen if we move a dislocation? So as I said, a dislocation, imagine here an edge dislocation, it will have a strain field around it, which has a compressive part and a tensional part. So if you combine the strain fields of two dislocations, imagine that they move close to each other, then you can have a repulsive action or you can have an attractive action. So they can be attractive for another, or they can be repulsive. And this depends on how the strain fields are related to each other. So if you have the combined strain field and it's larger than any of the singular strain fields, you will have a repulsive action. Whereas if you have a lower strain field in the combination, which is lower than any of the single ones, you will have an attractive action. What is always true is that you have obvious attraction if a tensile region approaches a compressive region, of course. And if they overlap, there will be no repulsion. And opposite Burgers vectors will always have, if they are laying in the same plane, of course, they will always have attractive action. It means that you can recombine dislocations and you can do something with them. And you heard about the dislocations from Geoff, what they are doing, because you can have these facets and these pads or these surface triangles maybe in the gallium nitride, and they offer an inclined surface, and you can move the dislocations to that because they can lower their line energy by shortening their line. They can have maybe a recombination action and so on. And Burgers vector with the same direction are always repulsive. So they do something, and this is what we see in the material. So they form clusters, they annihilate, they change their nature due to interaction. And this is something that is also relevant for what the dislocations do to an electronic device later on. Now we have left out the point defect so far, but the point defects is what we want if it is a doping atom. But the dislocation can also do something to the point defects. They can gather it, and gather means they grab it. And if you imagine the male crystal that you visualized before, and you send impurity atoms through this, so let's say the ladies would now be the doping atoms, and there is a positive attraction, they are all grabbed and pulled to one place. So the impurities, they can just supersaturate at a dislocation, and which acts as a nucleation site for just grabbing many of these impurity atoms. And the strain field itself is an attraction to get a point defect moved to a dislocation. So the dislocation cores, they have special energetic places. They can offer charges, dangling bonds, and so on, which is attractive for an atom. And under a temperature, which the processes are normally, you have some easy moving of some species, and then they just being attracted and go to a dislocation there. So the dislocations can be decorated with foreign atoms, which changes their nature and their electrical nature. And the neighbored material can be affected by this as well, because you can imagine that there is a depletion of atoms in the surrounding of such a gathering dislocation. So if you have dislocations present in the crystal on a microscopic scale, the properties can never be homogeneous, which is a problem for a semiconductor. So this is just how dislocation, there's a visualization of how impurities move to a dislocations, and I show you later in experimental data how this is really be seen in measurements. So there is an activation of an impurity to be gathered through thermal activation, and the impurities are being collected at the place of a dislocation. It can be wanted or unwanted, and you see here, for example, a grain boundary between two crystals. This is very typical for polycrystalline solar silicon, for example. And if you have many impurities here, which are the red dots, and you add some temperature and some process steps, they can move to such places where you have a large abundance of dislocations, and such they just collect the impurities and the dopant atoms with it as unwanted. And here you can see in an experimental data, which we did some time ago, this is a solar silicon, and we did some electron beam induced current measurements combined with the chemical analysis on the microscopic scale. You see here how the sample is mounted. So you have, with the electron beam induced current, you just light your material with the electron beam and introduce excess carriers, and you have a field where you separate the carriers, and if you flow them through the material, you see where no contrast is, do you have a constant current flow, and where you have a dark contrast, those places are catching the carriers and recombine them such that you have no current flow of the epi current, and this is what you see as a dark current here, as a dark contrast here. So this means that you have all these grain boundaries here, and the grain boundaries in that polycrystalline silicon are decorated with iron precipitates. It comes from the production process. And if you see this in an enlargement here, you see that there are small dots. And this is an SSRM picture, so a conductive AFM picture. And you see that the conductivity at those places is much different compared to the neighborhood where you have the two crystals. And if you analyze this, you find that any of those dots is containing iron, so it's an iron precipitate. And by such ways, we can identify what the dislocations or what crystal grain boundaries, for example, do and how they gather impurities. So what about the electrical properties of dislocations? So I showed you that the grain boundaries have electrical action. They can change their nature due to gathering of atoms, for example. And a grain boundary you consider as a number of many dislocations. It's just an array of dislocation, a grain boundary. So it's just an example what they do, but you can break it down to single dislocations as well. So the effect that a dislocation can have depends on its orientation with respect to a current flow, for example. It depends on its nature in the core, which gives you some charge of the dislocation. So the core structure defines the charge of the dislocation. So what I showed before is that a pure dislocation can have some properties, but it also changes maybe its properties due to what happens to the dislocation during the process step that it experiences. And I showed you that they can do something like they can react and form arrangement cells and so on. And those arrangements can have different effects or different properties compared to a single local isolated dislocation. So these are all the things that we have to consider. And gallium nitride is no different. So here I show you what the differences are in terms of these reaction, cell formation, and arrangements. You see a Casada Luminescence image. Casada Luminescence means you observe the light that is coming from, that is emitted from your material, which functions quite well in the gallium nitride since it's a direct bandgap semiconductor, so you can illuminate it with an electron beam and you collect the photons coming from it. And the dislocations, as I said before, dislocations act as, for example, non-radiative recombination centers, so they catch the carriers away, so they don't emit light in the case of the gallium nitride. So all the dark spots where no light is emitted is the places where the dislocations are. So here it's an example for gallium nitride on silicon with a dislocation density 10 to the 9. So this is produced in a hetero-epitaxy, and you see that the dislocations are not isolated. So the number of dislocations is large, and they accumulate. They can form lines here in the TM picture. You can see that they can form lines, they can form clusters, but there are also larger regions that are quite fine in terms of defects. But it means that the material on a microscopic scale is very inhomogeneous. Whereas if you watch a freestanding crystal with a dislocation density like 10 to the 6, you have these single randomly distributed dislocations. So you don't have effects that come from clustering, for example. So you only have to consider singular dislocations in that case. And this is the very difference. So the dislocations we don't want because any energetic level that exists in the bandgap of a semiconductor can act as a recombination path, and you saw it from the Casada Luminescence image that they do, and they can recombine carriers. So you have a niveau, which is the defect, of course, because your crystal lattice is not perfect anymore, and this offers you a radiation or non-radiative recombination path. And this is what we don't want. So the different core structures, for example, in a gallium nitride, if you now look at dislocations in gallium nitride, are different. So they can have different theoretical configurations. So most of them are negatively charged. And this is something why the gallium nitride functions at all. Because if you imagine a semiconductor with 10 to the 9 dislocations, and you think it would be silicon, or you would think it would be gallium arsenide, it would not function as an electronic material, really. And by surprise, the gallium nitride functions. And for a long time, the researchers asked themselves why the gallium nitride functions as a direct bandgap semiconductor, emitting light, or be usable as a power electronic medium, although it has 10 to the 9 dislocations. This is not typical for a semiconductor. And this is because of the nature of the dislocations in the gallium nitride. At least 2 configurations are thought to be neutral, and the electrical properties of the edge dislocations are different from the electrical properties of a screw dislocation, but all the experimental data, as you can imagine, does not fit perfectly to the theoretical assumptions that are made, because the analysis of such dislocations in their electrical nature is quite difficult. And it also depends on the generation of the material. So what history does the material has? What was the substrate where it was grown on? What is the process where it was grown with? What is the device process later on? How many temperature steps, at what temperatures it does experience, and so on. So all actions that I described before, like reactions, scattering, and so on, they are possible in gallium nitride. So we have to think about all those actions. And this is an example which just shows you what dislocations can do with respect to their dislocation type. So consider an edge-type dislocation and a current flow along the direction of the plane where the edge dislocations exist. And you measure the sheet resistance, for example, and you express the quality of the material, which is expressed in a full width of half max on a diffraction pattern. And it's just, let's say, a measure for the number of dislocation and the perfection of the lattice. And if you observe several diffraction conditions, you can distinguish between the screw dislocation and the edge-type dislocations. So what you see is, here's the crystal quality better, and the larger the numbers are, the worse the quality of the crystal is, and you see that the sheet resistance increases with increasing, let's say, worseness of the structure, with the increasing number of dislocations that you have. So, for example, a sheet resistance, which is an electrical parameter which is important, can vary due to edge dislocations and not to screw dislocations. Screw dislocations will just scatter, but edge dislocations have a different action in that case, and an effect on a lateral device or any lateral current flow along their direction. So if you consider what I said at the very beginning, that an electronic device is just a sequence of epitaxial layers. You have to deposit these epitaxial layers on something, and you heard from Jav that this is on silicon for the gallium nitride, and you have, as he explained, many layers that you need for strain and dislocation accommodation, and also for the function, for the design of the device. So you have a sequence of different layers, and at any let's say, interface, you have a mismatch between the materials, and dislocations can happen and can do something to the whole structure. And the starting material, so the substrate where you start on, whether it's silicon or a native type of substrate, makes a big difference. Why does it make a big difference? And I don't want to give you too much redundancies, so it's just in short. The aim is that the crystal layer should have no defects. This is what we said at the beginning. This would be the ideal case. So what we need would be a perfect structural match. So the substrate A and the epitaxial layer B should have no difference in their structures. This would mean you should have a native substrate case. And on the other hand, as you heard as well, we don't only have a perfect structural match, we also have a thermally match. So it means that you have a process which has many temperature steps that you're applying to the material if you produce it. And if you heat it up, cool it down, heat it up, cool it down, you have the issue with the thermal expansion coefficient. So if you only consider the structural mismatch between the substrate and the epitaxial layer, you have the native substrate case here with a perfect match, and you have the foreign substrate case here where the lattice on top of this, of the epitaxial layer, does not fit perfectly to the bottom, which is the substrate. So, and for the foreign substrate case, additionally, you have to consider the thermal expansion coefficients. So this is something that would only go away in the native substrate case, although we have all this discussion that it's too expensive and so on. So what shall we do for the gallium nitride? This is what it's not so easy. So homoepitaxy would be the best to attain defect-free perfect crystal structures. But therefore, we would need native epi-ready substrates. And now there is a different table here. You saw something like this before, but now it's a different focus. You see that there is different technology. The silicon technology with all the silicon devices is very well established. You have the silicon substrate. So you grow silicon devices on silicon. You have the crystal growth process available, which is very mature, so it gives you very perfect and cheap substrates in a large size. Now let's go to an example of a compound semiconductor, which is quite established, gallium arsenide. So the gallium arsenide technology uses gallium arsenide substrates. So the BGF technique to grow the gallium arsenide substrates, it's very well established. So it gives you good and cheap substrates up to 200 millimeter. So gallium arsenide is grown on gallium arsenide. Silicon carbide is grown on silicon carbide. Silicon carbide crystals are grown by a PVT process. It is a good quality, it is expensive, but it reaches 150 millimeters so far. What you can also see, the diameters are decreasing and the costs are increasing here with the establishment of the crystal growth process. Now we have the poor gallium nitride, which is the poor one, the most difficult one for the crystal growers, and you have different choices of substrate: silicon, silicon carbide, sapphire. And since no crystal growth process is really established, we don't have the choice to grow the gallium nitride on gallium nitride. But as a crystal grower, I'm convinced that physically it would be the right way to go, because you can see it here as well. But it's a problem with the availability, you have a problem with the prices, and so on. So in any case, for any semiconductor, it's only available if the crystal growth technique is available. So you need a technology which helps you to grow the crystal, and you need technological solutions for the wafering and polishing to produce the substrates. So this would be the ideal case. And this is why we go for the silicon, and this shows you how a better crystal should look like, and this is what I showed before, so we can go over this. You can see arrangements of dislocations, and if you lower the dislocation density, like from 10 to the 9, like 5 times 10 to the 8, like 10 to the 8, like 10 to the 6, you get more and more rid of these arrangements, which would help to get the crystal quality better in the epitaxial layers. So what about the reliability of power devices in relation to dislocations that are present? So here you can see an illumination, so it's just an electroluminescence picture of a gallium nitride layer, and you see that radiative and non-radiative recombination is different at different places, so it's by no means homogeneous, and this is also something that we don't want. So this is definitely a direct action of the presence of dislocations in a material. And here, for example, you see a transistor and you see some local warming, which can happen at those places where dislocations are. And in a cross-section, you see that underneath a gate contact, you can find a dislocation, which causes, of course, the failure of this device. And in that case, a catastrophic failure. So how can we identify the conductivity of defects, for example? And this is something I have stolen from Sven. He's doing conductive AFM technique, so he puts the AFM needle on top of a hemmed structure in this case, and it's conductively connected to the backside. So we put a potential to this, and we try to map the current flow vertically through that structure, and you can see that there are places where you see a different current flow compared to the surroundings, so it is still inhomogeneous current flow, with large regions like tens of micrometers, which show a lower current flow than the surrounding. And you can see if you enlarge this region, for example, these dark spots, and the dark spots, they are discrete spots of very high conductivity, and you can relate this to dislocations and to the majority of screw dislocations, or eventually of bundles of dislocations. Now, this is how we can visualize the action, what dislocations are doing to a crystal structure. So how can we understand what the defects are doing, or how they're responsible for vertical breakdown? So this is something that we did with Joff together. You see that there are current versus voltage curves, and we have two sets, let's say two groups of devices, and we call the ones the failed devices and the other ones the passed devices. And we try to investigate or determine what the critical defects are. And I can go over this. We do it by Casada Luminescence. And as you heard before, by Casada Luminescence, we can show where the recombination active regions are. And what we could show here is that the dislocations, in fact, get at the carbon, and this is some kind of an empirical model. So if you imagine that a dislocation forms a niveau in the bandgap, and let's say, an impurity or a dopant atom moves there, it means that you change the nature of the dislocations and you deplete the region in the vicinity here. And also the depleted region may change your electrical properties and the conduction type of the crystal, which you don't want, not only the singular dislocations. And if you have many dislocations which come close to each other, you can see at a density of 10 to the 9, which is about the interaction distance of the dislocations, which is then like 150 nanometers or some other value, you can see that the overlapping of such regions where you deplete the carbon, so where you have a direct action of a dislocation, is even more harmful than a single isolated dislocation. And this is another effect on the lifetime, which is expressed for laser devices here, versus dislocation density. And it was measured by Sumitomo some time ago, and you see that the dislocation density, which is high here, like 10 to the 9, and which is 10 to the 4 here, is dramatically increased if you lower the number of dislocations. And this is what we had before. So we learned that the substrate determines a lot, and it determines a lot the reliability and the performance of an electrical device. So what is the final conclusion? A semiconductor must be as perfect as possible, but no crystal exists without at least point defect. This is what we learned. The extended defects must be avoided as much as possible, which is, to my opinion, perfect if you use a homoepitaxial solution, so you have a native crystal as a substrate. And the hetero-epitaxy has strong consequences for the microstructure, and it will always be there as long as we are in this scenario. And the case of gallium nitride hetero-epitaxy, it works, but many defects are present, and they will have an effect, of course, on the device performance. And this is what we are researching for in this project also. I thank you for your attention.
Thank you very much, Elke. Any question for Elke? Okay, Peter, the podium is yours.
Thank you, Elke. Thank you. Thank you for referring to the male in the room as being a disturbance to you. It's an interesting way of looking at it. But so you convinced me that gallium nitride is very, very difficult to grow.
Yes.
But I was surprised to see in, I think, one of your slides that aluminum nitride was at the same level as silicon carbide. Or I misunderstood, maybe. So is aluminum nitride more difficult than silicon carbide? Or aluminum nitride?
It is more difficult than silicon carbide. So both of the nitrides are more difficult than silicon carbide. So many things in silicon carbide crystal growth are already established that are not for the nitrates. The aluminum nitride grow as a larger crystal has a different possibility due to the PVT process. And the PVT process is easier to be controlled than a chemical mediated process like the HVP growth. So the PVT growth process can produce better quality, and it does produce aluminum nitride crystals with a good quality and a decent size. On the other hand, it's more difficult to scale it up in larger areas. So if you want to have a 150 millimeter or 100 millimeter crystal. And this was also the case for the silicon carbide. The most challenging thing in the silicon carbide growth is now the scale up to 150 millimeters. This is easier, kind of easier, in an HVPE growth process with the gallium nitride. So it would be easier to attain a larger diameter compared to the aluminum nitride, which doesn't want to expand its diameter. On the other hand, the quality is poorer for the gallium nitride compared to the aluminum nitride as it is now.
But they solved it for the silicon carbide, so over time they will solve it for aluminum nitride as well.
Yes, yes, and over time we will solve it for the gallium nitride as well.
Yes, but if you will have aluminum nitride bulk crystal, why would you still need gallium nitride?
Yeah, this is a good question. I don't know. maybe if in the InRel project, where we're all in, the aluminum nitride will perform so well, then it outperforms the gallium nitride.
6 electron volt, huh?
Yes, 6 electron volt.
Okay.
And not monoclinic.
Okay. No other question from the audience, so let me thanks Elke again for the nice presentation.